Hi everyone. In this video, our objective is to use reference tables to predict products of double replacement reactions. Let's start by talking about what a double replacement reaction is. A double replacement reaction, also known as an exchange reaction or precipitation reaction, takes place when two compounds interchange elements to form new compounds. The general formula for this reaction is AX combining with BY yields AY and BX. If you notice, the A is now combined with the Y and the B is combined with the X on the product side. Now, in order for a double replacement reaction to take place, both of the reactants must be soluble in water. That means they will dissolve in water. Now, to tell if a compound is soluble, we have to read a solubility table that's on the next slide, or look for the designation AQ, which means aqueous. So, if we were to again put down AX, we might see a little AQ written here to suggest that that has been dissolved in water, and the BY would also carry that designation. All right, so on the reactant side, the substances must be soluble in water. Now, what we have to do next is compose the potential products. One product must be soluble, and one must be insoluble. That means it would become a solid, or it would fall out of solution. The insoluble product is the precipitate that forms when the reaction takes place. Usually a precipitate is a solid. Again, the table will help identify them. But let me write down our example from up here to show you what you would look for. So AY as a product. Now that one might be aqueous. And the BX, if it is a precipitate, it becomes a solid. So these are the things we're looking for. Let's dive a little deeper now. So now let's inspect that table that I spoke of earlier. And it is the table that talks about the solubility guidelines for aqueous solutions. So if something is soluble, it will dissolve in water. So it will break apart. We sometimes call it dissociate into the water. And this is aqueous. Aqueous suggests the water. Now, if it does not dissolve in water, yes, it could be a liquid like oil and water. Oil does not dissolve in water. But typically when we have these conversations, the substance will be a solid, and we call that a precipitate. All right, so let's inspect what this is telling us. Okay, so this says soluble compounds. So in our formulas of our compounds, if we notice a group 1 ion like lithium, sodium, or so forth, if it is present in the formula, the substance is soluble. Now, there are no exceptions. Let me show you where there are some exceptions. Down here we have our halides. If you notice chlorine in the formula, the substance will be soluble unless the other part of the formula has silver, lead, or mercury. So a good example of one that is soluble would be NaCl. Notice that it does not hit any of the exceptions. It is soluble in water. But AgCl, although it does have chlorine in it, because of this exception right here, it is insoluble and typically would be seen as a solid. Let's take a quick look at the other side of this, this table so we can understand it. Okay. And this one takes a slightly different perspective. All of these, if present in the formula, are insoluble unless combined with one of these other substances. So to give you an example, calcium, which is in group 2, calcium carbonate, would be insoluble because it does not fit any of these exceptions, so it would be solid. Sodium carbonate, on the other hand, okay, it is carbonate, so it is insoluble, but we have a group 1 element present in the sodium, which makes this now soluble. So it would become aqueous if placed in water. And the other, all these others down here follow the same logic. So let's go ahead and try a few of these and inspect this reactant side of an equation. Here we have calcium hydroxide. Now, is that soluble in water? Calcium, so that we are aware, is in group 2 right here. So if that is mentioned, we need to know that. And hydroxide, which is OH, is right here. It's a polyatomic ion that carries a -1 charge. All right, let's get that off our screen. And see, is calcium hydroxide soluble in water? Well, I do see hydroxide here, and hydroxides typically are insoluble unless they are in combination with any of these ions, and calcium is one of them. So, in fact, this is aqueous. It is soluble in water. Taking a look at hydrogen, what's this stuff? It's a polyatomic ion. Oh, there it is. Hydrogen phosphate. And all of these are insoluble, once again, unless there is a group 1, and that's where hydrogen lives. It is a group 1, so it is aqueous. Now, what are the potential products? Okay, so if there was a double replacement reaction, the calcium would now be bonded with the phosphate. And I'm curious, is that itself balanced? And calcium is in group 2, as I showed you, meaning that it will have a, I don't like that color, it will have a 2+ charge. And phosphate, as you can even see here, carries a 3- charge. If we do the crisscrossing, we would notice that to make the calcium phosphate balanced, it would be 3 calciums for every 2 phosphates. Now, what would be the other substance? The hydrogen with the hydroxide, which, by the way, is water. That's H2O. All right, so the question is, are either one of these substances insoluble in water, forming a precipitate, a solid? And let's inspect. This substance right here, again, is phosphate, phosphates. They are all insoluble unless they are in combination with these. So, group 1, or ammonium. So, phosphate. It is insoluble. So, it will become a solid. All right? And, of course, water is soluble in water. So, this reaction will occur. I'm going to push this now into the next slide so we could see that we also have to do some balancing here. So here, once again, is the double replacement reaction. It will occur. This substance was aqueous, aqueous, aqueous. Again, that means able to dissolve in water. And this one became a solid. So that identified our precipitate. But I do notice that this equation is now not balanced. So a method that we used before to balance equations is to identify the individual substances. And you're going to see a shortcut that I take here. We have calciums, oxygens, hydrogens, and I'm actually going to treat the phosphate as one substance, because on the left I see phosphates together and on the right I see phosphates together, so those ratios are not going to change. So it's going to allow me to do a little bit of a shortcut. And on the right I have calcium, oxygen, hydrogen, and again the phosphates. Now on the left I have, on the reactant side, 1 calcium, I'm going to ignore the oxygens that are in the phosphates because they're accounted for with the PO4. So in this location here, I have 2 oxygens. How many hydrogens total? I have 2 hydrogens from here and 3 here, giving me 5. How many phosphates? 1. On the right side, 3 calciums, 1 oxygen, and 2 hydrogens and 2 phosphates. So what can I do to adjust these numbers? What I can do first is try to balance the calciums. If I put a 3 coefficient here, this calcium becomes 3, and they match. What happens to the number of oxygens? The oxygens was 2, but now I tripled it. We are now at 6. And my hydrogens were 5. 3 from here, and now I have 6 from here. So I am at 11. Okay, on the right side, what can I do to bump this number up to 6? And what I can do is I can add a 6 here, which gives me now 6 oxygens on the right. Now what else did that do for me? How many hydrogens do I have? I now have 12. There's still an issue. So what else can I do? I can... Oh, I noticed my phosphates are not matched. And what I can do here is I can make that a 2. And now my phosphates match, but my hydrogens are off. So let's readjust the hydrogens. I have 6 hydrogens from here and an additional 6 from here. Oh, I guess my math was off earlier. It wasn't 11. Now it's 12. Reinspect, everything balances. Good job. All right, let's take a look at this one now. We have potassium carbonate, that's carbonate, so potassium carbonate combining with barium chloride. Barium chloride, where do we have? Barium is, let me take a look at my periodic table, is in group 2. Chlorine, oh, there's chlorine. So, chlorines are soluble if they are combined with anything except these. With barium is not one of the exceptions. It works, so this is soluble. Potassium chromate, there's my chromate. It is insoluble, but it is paired with a group 1 element being potassium. So both of these substances, these reactants, are soluble. Let's write down what the possibility is for the rearrangement, the double replacement. We could end up with potassium chloride with barium carbonate. Are these balanced in and of their own right? Potassium gets a +1, chlorine a -1, so that's a 1-to-1 ratio. Barium is a 2+, while carbonate's a 2-, and those ratios are fine. Now let's see. Remember the chlorides, the halides, chlorine. Chlorine is soluble unless it's with these, so this will be still aqueous. What about the barium chromate? The chromates are insoluble. They will all be solids unless combined with group 1s, and barium is a group 2. So this is solid. It is our precipitate. And in order to balance this, let me just cut right to the chase. We're going to have to add a 2 here. Inspect for yourself, but that is balanced, so that works.